All right, transistors A and G, Minkoff, College William and Mary, Week 6, transistors were invented in 1947 that amplify current, the lower power consumption, cheaper to mass production, robust vibration, long working of time, decades will probably use, replace vacuum tubes, building block of modern equipped electronics. Some areas use vacuum tubes are so good, ultra high voltage application more than 1,000 volts, radiation prone locations, negative, positive, negative transistor, collector, emitter, base. So we have the collector at the top, the base, and then the emitter follows the negative, positive transistor, collector, base, emitter. And these are shown in diode relationships too. Notation, base emitter current, or IBE. Collector emitter current, ICE. Base emitter voltage difference. Base voltage base emitter equals voltage base minus voltage emitter. Collector emitter voltage is voltage collector emitter equals voltage collector minus voltage emitter. And then over here it shows collection base emitter amps and base emitter current, amps and current to emitter. So simple negative, positive, negative, positive, negative transistor rules. Current shows direction. Simple negative transistor rules. Support showing current directions. Voltage current emitter is greater than 0. To support shown current directions, voltage current emitter is greater than 0. Voltage base emitter is greater than 0 since the forward bias of the voltage base emitter is equal to 0.6 volts. To support shown current direction, voltage current emitter is greater than 0. Voltage base emitter is greater than 0 since the forward bias of the voltage base emitter is congruently 0.6 volts. Voltage current base collector base is greater than 0. Since the reverse bias has no current goes from the collector to base, all current is directed to the emitter. Voltage collector base is less than 0. The transistor goes in saturation, cannot be described in the following simple rule. To support current the direction, voltage current emitter is greater than 0. Voltage base emitter is greater than 0. Since the forward bias of voltage base emitter is congruently 0.6 volts. Voltage collector and base is greater than 0. Since the reverse bias has no current give the collector to the base, all collector current is directed to an emitter. Voltage collector base is less than 0. Transistor goes to saturation, cannot be described in the following simple rule. If above holds true, then voltage current emitter is 0. Voltage base emitter is 0 since the forward bias is 0.6. Voltage collector emitter, since the reverse bias is no current with the collector base, all currents are saturation. Voltage collector current is because the saturation cannot be following the simple. Above holds true if the ampere current elector is equal to the beta ampere current ejector. A bipolar junction transistor is current amplifier. To support current direction, voltage current emitter is greater than 0. Voltage base emitter is greater than 0. Since the forward bias voltage base emitter is congruently 0.6 volt. So voltage current collector base is greater than 0. Since the reverse bias diode, no current goes from the collector to the base. All collector current goes directly to the emitter. If voltage current election base is less than 0, the transistor goes to saturation, cannot be described in the following steps. Rule above holds true. Ampere current collector emitter equals beta ampere base emitter with a bipolar junction transistor current amplifier static forward current transfer ratio beta, or sometimes HFE, is equal incrementally 100 to 200. Supporting shows that voltage current emitter is, and then we read the same. The top is the same, but the new rule is ampere emitter is equal to ampere base emitter plus collection, and ampere current collector base equal to beta plus 1 ampere base emitter congruently beta ampere base emitter. Alright, apply the same rules for the negative positive bipolar junction transistor. Must comply multiple current voltage of negative 1. Hence, the arrow indicates the direction in which the current is supposed to flow. The arrow always connects the base and the emitter. Remember, beta is not constant. It depends on many parameters. Temperature collector current varies with device to device, even in some batches. Good design should not depend on beta value. Current flow load resistor does not depend on load resistance. Ampere induction, ampere current, and beta amper base electric. Ampere induction is equal to ampere collector times beta base emitter times beta times voltage control minus 0.6 volts over resistor set. Current through the load resistor does not depend on load resistance. The actual sample of the bad design current through the load depends on beta. Current from the load resistor depends on load resistance. The actual sample of the bad design, since current through load depends on beta. Where you get voltage collector is both the constant current of the minus the resistor inductancy, ampere inductancy. Current through the load resistor depends on the depending on load resistance. The actual sample of the beta design current load through depends on beta. Remember that voltage collector must be greater than voltage base, thus cannot be bigger than the saturation current. Ampere saturation equal to max inductor and ampere inductance greater than or equal to voltage constant current minus voltage base over the resistor inductance, and congruently voltage constant current over the resistor inductance. Voltage constant current point of view, less schematic, is equivalent to the right one. Resistor transistor is equal to voltage collector over amp inductor equal to voltage constant current minus amp inductor resistor inductancy over amp inductancy. And that's a transistor or resistor. Transformer / resistor, and a different power. Transfer power, dissipation power, transportation power, base emitter plus collector emitter equals voltage base emitter, ampere base emitter plus voltage current emitter divided by, ampere current emitter. Transition power dissipation, power transistor plus power base.
Alright, we got cabbage and sausage. You have 2 slices of leftover pizza.
Alright.
And some beans. And you're supposed to eat some peas and some cabbage on New Year's Day.
Alright, I will do that. Transistor power dissipation. Power transistor equals the bottom power base emitter plus power collector emitter equals voltage power emitter amp times ampere base emitter plus voltage collector emitter times ampere collector emitter. So we derive that power transformation equals voltage is congruently voltage collector emitter amp collector emitter resistor transistor load over ampere squared load. Maximum power distribution of a transistor. Maximum power distribution transistor resistor transistor is equal to resistor inductance. Constant current sources of power dissipation. Maximum power transit is equal to voltage constant current volt squared times 4 to the resistance of the inductancy, where ampere's inductancy is equal to voltage constant current 2 times resistant inductancy. When properly designed outcome depends not only on reachable variations of beta. Recall typical betas are 100 to 200. Well, assume worst case scenario beta is 10. Notice that resistor inductance limit carrier collector current inductance. Ampere inductance equal to voltage constant current over resistor inductance, and then we have ampere base emitter is equal to voltage control minus 0.6 over the resistor base equal to ampere inductance over beta. Resistor base is less than equal to voltage control minus 6.6 volts over voltage constant current beta resistor inductance. Emitter flow voltage output is equal to voltage input minus 0.6 volts. Gain what? Gain what gain? Voltage output is equal to voltage input 0.6 volts emitter flow. We achieve the input impedance decrease the resistant inputs is equal to voltage input over the amperage base emitter equal congruently resistor inductor beta times beta plus 1. Voltage input source is not overloaded, but the load receives all required current as long as the collector power supply can support it. Alright, this is transistors week 6. Alright, we're still going to record week 6. Week 6, Transistors Part 1, Chapter 1, Transistors and Game. This week we introduce the transistors. Transistors for three-terminal device that can apply signal with increase the signal power to the price of the must also the price is that we must also supply DC power to it. Hence, it needs 3 terminals. Figure 6.1 shows the classic transistor package style. 3 terminals called the emitter, base, and collector. The base for the current control terminal is small, with the current entry for the control, but the big current flows through the collector. The emitter notation may seem odd, but remember the electrons actually carry most current, but then they have negative charge. Part of the current flowing from the collector of the emitter means the electrons are flowing from the emitter to the collector. In this chapter, we'll use the simply mode of the device to try understanding the rather complicated behavior that constitute continued semester will encounter with additional devices that require some sort of approximate model to describe their expected behavior, since there's always approximation real devices that will have certain shortcoming conditions where the model does not longer apply. Basic transistor model, basic transistor with essentially with 2 diodes being packed back to back. This seems like the silly thing to do, but diodes are not. The same current flows from one diode and provides the carrier to the carrier the current through the other part of the element. Then this is most basic form of transistor with a current amplifier. Is a current amplifier. Bipolar transistors with 2 basic types, negative, and positive. The current flowing from the negative transistor schematically accompanying figure 6.2 with the below with the current conventional positive that goes through the base terminal with the output of the emitter of the amplified current flow for the collector of the emitter. Our first model of the transistor set of the collector emitter current is beta time of the base emitter of the current. We'll see that the good design is dependent on the beta since the vary from one device to the next. If it depends on the operation condition of the temperature of the most transistors value with the beta of congruently 100. In the weak laboratory, we'll measure the beta of the 2N3904 transistor. Of the negative power of the negative transistor, current will flow over the base of the emitter only over the base voltage of the positive with respect to the emitter. Collector current will flow with the emitter only if the collector is positive with respect to the emitter, and if the positive and negative power of the transistors things are reversed, the current will flow with the emitter to base only if the base voltage is negative with respect to the emitter. The collector current will flow with the emitter only if the collector is negative with respect to the emitter. The arrow of the emitter tells which way the current is supposed to flow, which allows indication of the base and voltage positive and negative with respect to the collector. So for the negative power of the collector and the positive and negative collector. Let's summarize the condition required for the negative power of the negative transistor to conduct transitory rules. Voltage base emitter with a greater than 0, since the diode with the voltage base emitter should be roughly 0.6 volt. For the conducting voltage base collector is less than 0. Back bias diode with enough voltage for the base current normally flow with the emitter. They do not want the current to flow for the base of the collector. Ampere current emitter is equal to beta ampere base emitter. Under normal operation conditions, we'll have a resistor or load connected to the emitter of the collector. Will voltage drop off the load with the collector emitter flow with the root of the transistor. If the collector emitter changes the voltage drop off the transistor voltage collector emitter. If the voltage collector emitter drops too low, the voltage base collector will become positive. Since the voltage base emitter must still roughly 0.6 volts currently flow for the base collector, leading to the apparent drop of the bit of this is called saturation. 2. The base transistor circuits have some basic circuits for the illustrative of the operation transistor is a constant current source. The constant current source of the simplest transistor circuit possible, shown in figure 3 below. You simply drive with a small current and an ampere base emitter of the base of the transistor and produce the large current with the ampere current emitter through the rest of the circuit. In the case of the base emitter is given voltage positive, the E minus voltage base emitter is equal to ampere base emitter times the resistor base. The current through the load can be calculated with the other current from our current gain model amp collector emitter with a beta ampere base emitter. From this, if the current flowing from the load does not depend on the load resistance, depends on the bed of the design, on actual initial design. Current flowing through the load should be the independent load resistance flow with the resistor too big with the root with the voltage drop across the load with the voltage collector base too big too small with the conduct. In this case, the collector emitter will drop with the transistor surface the conducting again with the reduced effect of the beta with the transistor from the base current flows with the director collector. This condition is called saturation. Figure 6.3 shows the basic negative positive negative transistor of current source. Transistor switch. We can use the transistor switch to control the big control of the small current, but this is the current source of the device you wish to the switch and place with the low resistor with a common application of the digital 0 to 5 volt signal with a moderate impedance for the control of the device with the regulating requiring a lot more power. And the next week we will use a 5 volt TTL transistor logic output function generator to drive a light bulb. The design transistor switch with the must voltage drops across of the device. If the voltage common emitter is large enough, power dissipated inside of the transistor with the ampere current emitter, voltage current emitter will destroy the transistor. You can get around this by designing the switch for the saturated operation. Switch for the runs for the saturation mode. Some of the basic current of the flow of the collector ampere currently beta will be smaller than nominal 100. Or commonly designed strategy to design generous base current which could be satisfied with the effective gain of roughly 10. See the emitter follower amplifier, the most important circuit of the chapter for the emitter follower. This is very easy. Circuit with the design normal operation condition does not depending on the beta with the input voltage of the base produced with the base current with the amplifier with the collector current generated voltage dropped across with the emitter resistor. Both the voltage emitter cannot increase beyond the voltage input with the minus 0.6 volt with the base current will drop with the constantly circuit that produces the voltage input minus 0.6 volts and output. In other words, the output with the emitter follow with the input. In fact, for the simple rule, voltage base emitter is equal to 0.6 volts. Is usually significant to understand most transistor circuits. The emitter follower is extremely useful because of the transformer impedance for the current application over the transistor means that they can drive low impedance while pulling out small current with the source. This is just allowing of the transformer without transformer voltage. In the lab, you will build an emitter follower measuring the impedance that should find voltage out over the voltage source equal to 1 over the 1 plus beta. Derivation of the formula is left to the reader. D, the inverting and amplifier. The final and show that the 6.4 shows the classic emitter follower amplifier circuit. The final circuit of the inverter amplifier with the common collector shown in figure 6.5 with the inverter amplifier similar emulator follower with a 2-chain with additional resistor between the power supply and the collector with the output with the collector terminal with the, of course, transistor rules still force the emitter of the voltage input negative 0 minus 0.6 volts. This will set with the transistor called the voltage input of the minus 0.6 volts of the resistor emitter. When the current passes through the collector, the resistor generate the voltage drop of the resistor current collector is a time of the voltage input and minus 0.6 volts over the resistor emitter, which means the voltage drops off the control over the resistor will approximate negative resistor collector over resistor emitter times the input with the voltage output is given. Voltage output equals voltage constant current minus resistor collector over the resistor emitter times voltage input minus 0.6 volt with the minus sign means that the voltage base with the 0 with the collector with the read of the full supply with the voltage. The voltage also at the base is their big current collector voltage drop almost 0 with thus the output with exactly opposite of the input with the 5 and the distributing. You can use the 2 inverting amplifiers in series to get the non-inverting amplifier. Design exercises and then it has a lab to it, but we are not in class. We're just reading some of these notes from a college course.